Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, find the minimum diameter after merging two trees. The problem is very interesting application of in-out dynamic programming. If you have watched any of the previous videos in this channel about in-out DP, you can pause the video right here, take that as a hint and try to solve it by yourself. If you haven't watched this, you can watch this entire video, and I would link other videos in the description down below so that you can solve those problems as a follow-up. So with that, let's get started. The problem states that you are given two unrated trees n and m with n and m nodes, and you are given edges 1 which contain the edges of the first tree, edges 2 which contain the edges of the second tree. Now you must connect one node from the first tree with another node from the second tree with an edge. You have to return the minimum possible diameter of the resulting tree, right? So the problem basically is you need to merge two trees with an edge, and you have to do it such that the final diameter is minimum possible. So before solving this problem, what is the diameter of a tree, or if given a tree, how to figure out its diameter? That's a very standard problem. There are various ways to solve this problem. One of the easiest ways is you start with any node of the tree, right? Figure out the farthest node from this tree. In this case, any of these four nodes is the farthest node. Now start a DFS or BFS from this node itself, and then figure out the farthest node from this node itself, right? So two DFS, one from any node, figure out the farthest node, and then whatever is the farthest node you achieve, run the DFS from there and figure out the farthest node from that node using the DFS, and that will give you the diameter. Now why this would work, will not be covering that in this video, but if you want to learn more about it, this code forces blog is a very good blog that goes into the mathematical proof of why this particular solution works. I would link this in the description down below. You can read it. If you have any issues in understanding this, we can discuss in the comment section below. So now that we know what is the diameter of the tree, the problem asks that you are given these two trees, right? You need to merge these two trees with a single edge. Notice that if you add just a single edge, these two trees will be merged into a single tree, right? Now once you have merged, or you have to merge such that the diameter is minimum possible. Now what's the brute force way to approach this? Brute force way would be, okay, I will try to merge each node from here to each node in the right and figure out the diameter of each of those possible trees. Whichever gives me the minimum diameter, that will be my answer, right? So what you will do, you can start with, okay, I will connect this node to this node. Now this is an entire tree. We will figure out the diameter using the exact same algorithm we discussed just a while ago and note down its diameter. Now I will try out another tree which is, let's say, connecting this node to this node, figure out the diameter, note down its diameter, and so on and so forth. We'll do this for all the trees and return the one with the minimum diameter. What's the overall time complexity? First of all, we are trying to merge every node from the left to every node in the right. So total number of trees that will be forming will be n cross m, assuming that n is the number of nodes in the left tree, m is the number of nodes in the right tree. Now after you have formed a tree, let's say this tree, what you are doing, you are trying to figure out the diameter, and as we discussed, diameter requires you to do a DFS or BFS twice. So basically that will take you order n plus m time, right? Because number of node would in the new tree would be n plus m. So this is the overall time complexity of the brute force algorithm we have, right? And obviously this will not pass because the value of n and m both is 10 power 5. So we need to optimize this. So we can try to optimize this one or this sector or this factor. Which one we should start with? Let's start with one of these two. Why? Because we are sure that these two must not be here. In other words, we are not, or we can't afford trying out every possible tree, and removing any one of these is a symmetric problem. In other words, let's say you say, okay, for this node I will connect this node with all possible nodes in the right. First this, then maybe this, then maybe this, and so on and so forth. Now instead of connecting every node in the right, if I am at a node, I need to figure out which of these nodes will give me the best result, or in other words, if I chose a node in the left, connecting which of these nodes would give me the minimum diameter, right? So would encourage you to pause for a moment and trying to think by yourself. So let's say you connect this node and this node. What is the diameter of this entire tree? Diameter can either lie completely within this tree, like this can be a diameter, right? Or diameter can lie completely inside this tree, this can be a diameter. Or diameter can cross this edge and combine these two trees to form a diameter, right? Some nodes from left, some nodes from right to form a diameter. Now if the diameter of this entire tree lies in the complete left, we don't need to worry about anything here because this we already know. Similarly, if diameter lies completely in the right half, this we already know. The only thing that we don't know about is what's the diameter, or in other words, what's the farthest two nodes if we consider this edge as a must, right? So what will be the farthest node, or what will be the diameter if you consider this edge? Notice that this edge is connecting these two nodes, right? So if you have to consider this edge, these two nodes will be considered, and once this node is considered, you can simply say that whatever is the farthest node from here in the left tree and whatever is the farthest node from here in the right tree, if you combine those two, that will give you the diameter, right? In other words, if you consider any other path which is in this tree and is crossing this node, those paths will be smaller than the farthest path from this node, right? Similarly, if you consider any path that is touching this node and in the right half, that path would be smaller than the farthest path from this node. And if you consider these two farthest paths and just take them into the diameter, that will be the longest path possible that is containing this new edge that you just formed, right? So what you know the farthest path if you consider this edge, you know the farthest path if you don't consider this edge in the left half and in the right half. So your diameter would simply be a max of these three values, right? So the maximum, the farthest two nodes in the left half you already know, the farthest two nodes in the right half you already know, and to figure out the farthest path with this edge, we kind of know that we just need to find out what is the farthest node from this node X and what is the farthest node from this node Y. If we can figure out that, we can simply figure out the final diameter in maybe let's just order one time, right? So the thing is, we need to figure, like, this can be any node in this tree and this also can be any node in this tree. So in other words, you need to figure out what is the farthest node from every node here, right? So let's say you have this array already. How to build this array, we'll come to that, but let's say you have this entire array already which says you what is the farthest node from X, or rather what is the distance of the farthest node from X. Similarly, let's say you have this array already with you which for the right tree as well, which again gives you what is the farthest node, or what is the distance of the farthest node from y. So you can simply take these two, sum them up, and that will be your answer, right? Now, this was not the original problem. Original problem was we were trying to figure out which of the y's is the best for this x. So if you consider this y, then this will be the tree formed, right? Similarly, if you consider this y, this will be the tree formed. So which of these y is the best for this x? Now think about it. No matter what the y is, the final distance would be maximum of whatever is the diameter in the left tree, comma, whatever is the diameter in the right tree, comma, the farthest node, let's denote it by f, farthest node from x plus farthest node from y plus 1 maybe, right? So this will be your final diameter and you need to minimize this. So this is fixed, right? You can't change this. This is also fixed, you can't change this. Now for a particular x, this is also fixed, you can't change this. Plus 1 is fixed, you can't change this. The only variable is fy, and that depends on which node you are taking. And what is fy? Fy is one of the values in this array, right? Which is basically the farthest node from a particular node y in the right tree. So what will be your best y? Best y would simply be the minimum, the y with the minimum value of fy. Why? Because you want to minimize this entire expression, and this entire expression will be minimized if this entire thing is minimized, right? And to minimize the entire thing, you need fy to be minimum possible, right? So what we just discovered is, if for a given x, we don't need to iterate over all the y, the best y would always be the y which is to which the farthest node value is minimum possible in this array, right? So you figure out the value of y. Let's say you calculated this entire array already, as we discussed. How to calculate this will come to this, but let's say you have this entire thing calculated. So you can simply figure out this y by just iterating over this array, and this y would be exactly equals to any of the other x you consider. For this x as well, this y will be the minimum possible. For this x as well, the same y will be the minimum possible, because notice that for everything you have just one variable fy, and that will be minimum at a single value in this array. So for every possible x here, you will have the exact same y as the best value, right? So with this exercise, what we have done, we have reduced this entire m altogether, and we are saying that we'll just simply iterate over all the x, and we will know the diameter of this entire tree in just order 1 time using these two values. So this entire thing also will go away, right? So our entire algorithm is order n plus f of n and f of m, where f of n is the calculating the farthest node for every node in the left tree, calculating the farthest node for every node in the right tree, right? And this is a feasible solution only if n and m, if we can simply optimize n and m completely, or figure out an fn and fm in less than order n cross m time, right? So we'll come to that, but for now we can also see that we don't need to iterate over all x and all y. No, remember that the problem of n and m are symmetric, right? If you have chosen that, okay, I will iterate over all the y's and I will figure out what is the best x for every y, the problem would exactly be the same. In that case, f of y would be constant, and you will be having f of x as a variable, and f of x would be minimized at a point x which gives the minimum value in this particular array. And that f of that x will be same for every possible y here, right? So in other words, what we are saying is we even don't need to iterate over all possible value of x, rather we will figure out what is the minimum value or minimum index where the value is minimum. What is the index where the value is minimum in the right half? We will simply connect those two nodes, and that will be giving us the minimum possible diameter, right? So instead of trying out all possible n cross m combination, we now exactly know what is the combination that will give us the minimum diameter. Now once we have figured this out, the problem is just figuring out the diameter, which we can simply do either by algorithm, or we already know what's the value of the diameter, which is dl dr fx plus fy plus 1. Fx and fy will get from this, and dl and dr we can compute with the with any algorithm to figure out the diameter, right? So only question that remains is how to figure out fn and fm efficiently, or rather how to figure out these two arrays efficiently. So let's tackle that. Now we need to figure out the farthest node for every node. What is the farthest node, right? We have solved this problem, or this is the exact problem which can be solved using in-out dp. We already have solved, I think, 2 or 3 times in this channel. This is like one of the videos where we discussed a simpler version or simpler problem with in-out dp. This is the video which I got where we discussed a slightly harder version with in-out dp. So after watching this video, I would encourage you to definitely try out at least one of those 2 problems to strengthen your understanding. Now let's come back here. We need to figure out for every node what is the farthest node. So again, what's the brute force solution? Brute force solution could be, okay, you start DFS or BFS from this node of the tree, and you get the what is the farthest node from this node, right, with simple one BFS or DFS. So that will take you order n time for a single node, right? Now you want to figure out the farthest node for every other node, like for every node in the tree. So if you do this exact same exercise, you will be taking you will be rooting the tree at different nodes. So currently we have rooted the tree at this particular node, but then there are various possible configuration. Like for example, you can root the tree at this node and it will look like this, right? Similarly, you can root the tree at maybe this node, right, and this will look like this. So basically you have to root the tree at every node and then run BFS or DFS to figure out the farthest node, right? And if you do this, the complexity of calculating that f array or farthest node for every node will be order n square, because for every node you are running a DFS or BFS which will take you order n time, and you're doing it for all the n nodes, and hence order n square, right? But we can't afford this because this would simply mean order n square plus order m square, and this will be no better than order n cross n, right? So we need to optimize this. Now how to optimize this? Notice there are 2 n's. One, we are doing DFS. One is coming from the fact that we are doing DFS for every node. So obviously we need to do at least one DFS or BFS. So the only thing that we can optimize here is we shouldn't do DFS or BFS for every node. We should instead figure out a way to find the farthest node for every node without doing an explicit DFS for that node, right? So let's tackle that problem. Now first of all, what is the value of or what do you know about this tree? First of all, with one DFS you will know what is the farthest node from this node, and not only that, you will also know what is the farthest node from this node in the downside. Similarly, you will also know what is the farthest node from this node in the down of the tree. you will also know what is the farthest node from this node in the down of the tree, right? Because when you will be running DFS, you will say, okay, what is the farthest node from this node? You will say whatever is the farthest node from this node in the downside plus 1, or whatever is the farthest node from this node in the downside plus 1, or whatever is the farthest node from the downside of this node plus 1. So whichever is the maximum, that you will take as a value here, which is the farthest node from this node. So what you are doing is you are now computing what is the farthest node from this node in the downside, what is the farthest node from this node in the downside, and so on and so forth. Now while computing this, you will do the exact same thing. You will say, okay, what is the farthest node from this node in the downside, farthest node from this node in the downside, and farthest node from this node in the downside. And for each of these, you know the answer, because these are the leaf node, there is no other node below it. So you know that there is just one node that exists if you start from here. So for this node, what is the answer? Answer would be maximum across all of these plus 1, which is simply 2. For this node, again, this will be 2 because this will be 1. And for this node, the value would be 1. And finally, for this node, the value would be 3, right? So what does 3 mean? 3 mean that there are 3 nodes which, or if you go to the farthest node, there will be 3 nodes in between, 1, 2 and 3, right? So with just one DFS, you got what is the farthest node from this node, what is the farthest node from this node in the downside, right? So let's say you want to figure out what is the farthest node from this node in this entire tree, right? Currently you know that 2 is the value for this part, but you want to know what is the value for this node in this entire tree, and for that you need to root the tree at that node, right? So one of the way would be like you rooted the tree at this node, right, and you figure out the DFS. So for this tree, you want the farthest node. Currently you know what is the farthest node in this part, so what you don't know is what is the farthest node in this area. And what this area is everything outside of this downside, right? So if you can somehow figure out what is the farthest node going out from this node to its parent, then you can compute the farthest node for this node for this entire tree as well, right? Just to iterate, with just one DFS, we got farthest node from every node but to the down of it. Now because only one node has everything to the down of it, this node has the correct value of the farthest node possible. But for every other node, let's say for this node, you got what is the farthest node to the down of it, but what you are missing for this node is what is the farthest node to the up of it. And if you can figure out that, you can get the answer, final answer for this node as well. So let's do that. We now need to figure out what is the farthest node going out from the current node, right? We just rooted the tree at one node. Now we are figuring out what is the farthest node going out from that node. So which node is simplest to calculate? The root node, because there is nothing going out from this root node. So the farthest node that is going out from root node is 0, right? Or rather, there is the distance between the farthest node going out from root node is 0. Now once you compute this, you can compute this as well, or rather this or this. Why? Because if you, let's just focus on this node first. Now what can happen? You are going out and figuring out what is the farthest node from this node. So either the farthest node will follow this path, or the farthest node will follow this path, or the farthest node will follow this path, right? These are the only 3 paths. In other words, the farthest node would either be one of the child of the parent node or the parent of the parent node. These are the only ways you can get the farthest node from this node. Now, if you know the values of these three paths with you, you can just take the maximum and you will get what is the farthest node going out from this node as well. And do you know it? Answer is yes. For this path, you already know what is the farthest node because this is nothing but going down. Similarly, for this path, you already know what is the farthest node because this is nothing but what is the farthest node going down. Similarly, for this node, you know what is the farthest node going out from this node because that's something you have already calculated. So you know the value of all these three paths, you can take the maximum and that will be the value here, right? So let's look at that in action. We want to figure out, like we already know the value of this one, which is 0, right? Now we want to figure out the value of this, this and this. So let's look at it one by one. So let's first figure out the value of this particular node. And if you notice, we will just focus on the immediate children of the parent because none of the other things matter at this stage, right? So we have just cut the tree and said that okay, we want to figure out the farthest node from this node which is going out. Now we already know what is the farthest node from this node going down, which is like 2 nodes away, right? In other words, there is just one node below it and one node here. Similarly, we already know what is the farthest node from this node going down, which is just one node away, or rather there is no node below it. And similarly, we already know what is the farthest node going out from this node, which is 0 nodes away, right? Now, what is the farthest node from this node going out? Again, it can take either this path or this path or this path. So what is the maximum value across all these paths? It will be 2 plus 1, which is 3 nodes in total if you follow this path. 1 plus 1, again 2 nodes in total if you follow this path. 0 plus 1, which is 1 node in total if you follow this path. So which of these paths you will take? The maximum one, which is 3. So rather you will say the farthest node going out from here is at a distance of 3 nodes, right? Again, this 3 node, you haven't considered this node at all. This 3 node are apart from this node. What are the other nodes that you can go through if you want to go through the farthest node? So going out, the value of this node is 3. Let's figure out the farthest node from this node going out, going out. So, or going up. Again, this can follow one of these 3 paths and you know the value of all these paths. For this path, the value is 2 plus 1 again for this node because 2 is the node going down and there is one parent node as well. So total 3 nodes are there. So either 3 or 1 plus 1, which is 2, or 0 plus 1, which is 1. So maximum of 3 to 1, which is 3. So you will say maximum farthest node going out from here is at a distance of 3. Again, this 3 doesn't contain this node at all. Rather it says apart from this node, there are 3 other nodes. Now finally for this one as well, you will do the exact same thing. You will say what is the farthest node if you go out from here. So let's look at this one. Again, there are 3 paths. Either you will go this route, or you will go this route, or you will go this route. One of these will give you the farthest node, and you know the value of all of these 3. 2 plus 1, 3, 2 plus 1, 3, and 0 plus 1, 1. So the maximum is 3. So they will say the farthest node going out from this node is at a distance of 3, right? So once you know the value of root, you can compute everything that is the immediate children of root. Now once at this state, what you know is this thing. You know the farthest node going out from this node is at distance 0. The farthest node going out from this node is at distance 3. Farthest node going out from this node is at distance 3. Farthest node going out from this node is at distance 3 as well. Now once you know the value of this, you can compute the value of all these 3, and once you know the value of this, you can compute the value of all these nodes as well, right? So let's look at one last example. Let's say you know the value of this. Now you want to compute the value of these three nodes, or rather let's just focus on this node for now. So what you want to find the value of this node, right? Again, we will just focus on the immediate parent. So let's just break down the tree and focus on just these four nodes. So you want to figure out the farthest node starting from this node going out. So the farthest node can follow this path, or it can follow this path, or it can follow this path. So if it follow this path, the farthest node would be at 1 plus 1 distance 2. If it follow this path, the farthest node will be 1 plus 1 distance 2. If it follow this path, the farthest node would be at 3 plus 1, which is 4. Again, why plus 1? Because remember, this 3 doesn't count this node at all. It just says what is the farthest node, what is the distance to the farthest node apart from this node going out, right? That's what we computed just a while ago in this part, right? You can rewind and watch if you don't understand, but overall you will take the max across these three and you will get 4. So the farthest node going out from this node will be at a distance of 4. Again, this 4 doesn't contain or include this node at all, right? So this is the way you figure out the farthest node going out from every node, right? Now let's say you have all these values, right? So I will just note it down. This would simply be 4 4 4, and this would be 4 as well, and finally, yeah, this doesn't have anything. So these are the values. Now what did you get from this value? You get what you wanted. What is the farthest node from every possible node without doing the DFS for every possible node. Why? Because let's talk about this node again. So for this node, you already know what is the farthest node if you go down to any of the node, and you already know what is the farthest node if you go out, right? So in other words, if you just visualize this as a tree rooted at here, that is, this entire thing comes as a child of this, you know what is the farthest node in this path, you know what is the farthest node in this path, you know what is the farthest node in this path, and you know what is the farthest node in this path. In other words, you know what is the farthest node in all the paths. You can just take the maximum across all of them, and that will give you the farthest node across all the paths rooted at 2, and that's what you want. What is the farthest node starting at this particular node, right? And in the same fashion, you will get the value for this one as well. That is, 1 is the value for everything down and 4 is the value for everything up. So the farthest node from this node would be at a distance of 4, or in other words, will contain 4 plus 1 5 nodes in total, right? So that's the entire algorithm. Now what's the time complexity of this entire algorithm? What you are doing for each node, what we first did, we first figured out the farthest node if you go down, right? And that was just a simple DFS. So that will take you order in time, right? Now after that, what we did, for each node we calculated what is the farthest node going out, and for root node we already know that that's just order 1 time, right? Now for this node, or for everything that is immediate children of root, what we did, for each of them we figured out what is the farthest node from root that contain apart from this child, consider every other child, give me the farthest node from root, and I will also take maximum of that with what is going out. That's what you are doing, right? So let's first write the pseudocode. That will make things a bit more clear. So this is how the pseudocode look like. Now just look at the pseudocode, which we are just doing exact same thing. We are simply going over all the child, pushing everything here. You will, let's say, sort the answer as well, because you wanted for every path that exists, you wanted the maximum one. So let's say you sort this everything as well, and for each child, what you're doing, you are going in each, like for each child you are going and figuring out what is the in max. In other words, for this child, if you want to figure out the maximum value going out, you go to the parent, figure out what is the maximum in except this, right? So maximum across these two and maximum with this, right? So you take maximum of all values of child except the current one child, and the final value would simply be whatever you got from inmax plus 1 or out of src plus 1, right? Basically out of the root plus 1. So if you look this entire thing, sorting is not really required, but let's say you sorted it, that's also fine, because if you sort this for all the nodes exactly once, that will simply take you order n log n time, not n square log n. Why? I would leave that as an exercise for you. Just try to enumerate this for all the children and you will figure out why it is simply n log n. Now we figured out this part for every node, and this part for every node is anyways order n. Now only thing that remains is this calculation for every node. And how to do this? You are doing, like, if you do it in naive fashion, that will take you order c time for every node, and that will be order n square, right? But you can do it smartly. How? You can just select the top 2 max, and or rather you, let's say you select the maximum value always, and when you reach the maximum value, when you want to compute the value for the maximum value node, you just take everything except that and figure out the max value again. Or rather, in simple words, you just need 2 maximum, the overall maximum and the maximum without the maximum, right? So just think about it a bit. I'm very sure you will get it. But overall, if you look at this will also be simply order 1 for each node, and overall you will have order n for this entire loop as well. So order n log n for here, order n for here, order n for here, and the overall complexity is still order n log n. Again, this order n log n, you can simply make it order n by just selecting the top 2 values instead of sorting out all the values together, right? So, but for now we know that this entire thing, or figuring out the out value for this entire tree, is an efficient operation which you can do in less than order n square time, right? Now what you know is what is the out value for every node and what is the in value for every node, and you can simply take maximum for out and in to get what is the farthest node from every node. So let's just take one small example. What I've done here is whatever is written inside the circle is the maximum in value which we computed in the very beginning. Whatever is written in the arrow that is going out, that's the maximum out value, right? Now this entire thing you will compute with the 2 DFAs that we just discussed a while ago. Now once you have this, what you wanted was what is the farthest node for every node here, right? So let's calculate the farthest node for this node. So farthest node for this node would be, ideally you will not take this at all for this node, because this entire down part contains the entire tree, and that's also evident here. The farthest node going out is simply 0, right? There is no node outside, and the farthest node from this node would simply be at a distance of 3. And notice this time 3 means that there are 3 nodes between the farthest node and the current node, right? Now let's talk about this farthest node from this node. If you take the down part, then you will have 2 nodes between the farthest, you have distance of 2 from the farthest node to this node, including this node, right? So distance of 2, or if you go out, you will have 3 nodes distance from this node to the farthest node. So which one is better, 2 or 3 plus 1 4? Like why plus 1? Because notice you didn't included this node in this calculation. You can rewind the video and watch that why, but this 3 doesn't contain this node at all, and hence you will do 3 plus 1, which is 4. So farthest node would be either 2 or 4, whichever is maximum. So 4 is maximum, so the farthest node is 4. Similarly, for these, the farthest node would either be at a distance of 1 or 4 plus 1, 5. So 5 is greater, so 5, 5, 5, 5, 5. And for this one, again, farthest node going down is 2, or going up is 3 plus 1, 4. So 2, 4, 4 is the maximum. And simply for this one as well, 4 is the maximum. Now, what is the value here? This is the value for the F array we were discussing in the very beginning of this video, which is this array. So you got this array for this tree and this tree as well. Now once you got these values, you can figure out which of the node is giving the minimum value of F, and hence you will figure out X and Y, which in turn means which two nodes you should join to get the minimum diameter. And once you have X and Y with you, you can simply figure out Fx plus Fy plus 1. You already know DL and DR. You can simply take maximum across all of them, and that will be your minimum possible diameter, right? So hope this entire solution is clear. I have already shown you the pseudo code for both outward and inward as well. Inward we haven't seen, but that's just simple DFS. We have done the dry run of that as well. So would encourage you to pause and try to code this entire thing by yourself and get it accepted. If you're not able to get it accepted, it means there must be something which you don't understand. So you should come back, watch the video, and make sure you understand the part which you are missing. And as I mentioned in the beginning, there are other videos in the channel as well, in which we discuss this exact same trick of in-out. I will link at least these two videos. I didn't find other one. I think there was one more video as well, but I will try to find it and link it in the description below. But at least these two videos you can watch, or at least read the problem and try to solve it by yourself. And if not, you can watch the video as well. That will surely help you understand and appreciate how beautiful this technique is for this in-out DP. So next, we're looking at the code. Again, strongly encourage you to try it at least once by yourself before going forward. So the code is exactly what we discussed. We figured out the maximum depth, or maximum depth is basically what is the maximum depth for every node in this graph, right? So we figure out the value of F for the first graph, value of F for the second graph or second tree. We take the maximum across all the values of F, and that will be the diameter as well. Like this F must contain diameter. Why? Because what is diameter? Diameter is maximum distance between this node, between two nodes, right? Let's say these two nodes. Let's say this is the diameter. So this diameter basically definition is what is the maximum distance between these two nodes, right? In other words, you are saying that this F array for this node will contain what is the maximum distance from this node to any other node in the tree, and that is exactly what diameter would be, right? So for one of these, diameter will go through one of these node for sure, right? As the like starting node, and for this node you already know what is the maximum distance between this node and any other node in the tree, and hence the value of that node would be the value of diameter as well, right? So that's why we haven't figured out DL and DR in this solution separately by doing one more like two more DFS. Instead, we simply take the maximum across all of the values of the depth to get the diameter as well, because that will contain diameter as well. Now we figured out the answer contained the maximum across DL and DR. Now we have to figure out Fx and Fy and then join plus 1 as well. So what we did, we simply figured out the minimum index in the first depth, minimum index in the second depth. Now depth 1 of min index, depth 2 of min index will give us the maximum, will give us the number of nodes as well. Now I haven't done plus 1 because the value of Fx contains all the nodes here, right? And if we have all the nodes, like we already have one extra edge here, so you need to subtract -1 at the answer. Again, this is very small part. You will just try to figure out the value of number of nodes itself. You will itself figure out why -1 is required here, right? So Now let's look at max depth. We are doing two things here. We prepare the graph. This is like simply preparing the undated graph. We did the calculation of in, we did the calculation of out, and once we have done that, we just figure out the maximum from in and out, and that will be our answer, right? Now what is the in calculation? That's very simple. We'll simply go to each node. That's the minimum value that node can have because there is just one node, right? We'll go to each of these children and we'll try to figure out what is the maximum depth for the children, right? Once you have the maximum depth for the children, you will take the maximum of that with the current node as well, and this in of SRC will contain what is the maximum depth for from this node to any node in the children, right? Now let's look at out. Out calculation is also very similar. We push everything in the down array for every node. So notice that for out calculation, what you need to do, we have to, for each node, we have to go through the maximum of in for every other node and maximum, and take the maximum of that with the out value as well, right? So we go to in all the in nodes. Notice that all the in nodes, we are not skipping anything here. We sort it out, then we figure out the first max and the second max, right? Why we are at 2 zeros? I would leave that in exercise. That is simply because we should not get index out of bound exception from here. I think 1 0 would also work, but anyways, after this you have max 1 and max 2, which basically says what is the maximum across all of these and what is the second maximum across all of this, right? Now you go to each of the children. Now it's time to calculate the value for children. So what is the value? Value would be maximum across everything except this, right? Now if this 2 is not the maximum, then you already know that whatever is the maximum is the maximum across all of the other nodes as well, right? So we simply check if the current value is the maximum. If it is, we'll take max 2, otherwise we'll take max 1 itself, right? Simple. Now we got max in. Similarly, we also know max out already, because if we come here, we have assumed that the parent value is already computed. Then that's when we'll come here, right? That's the algorithm. Now we'll simply take the maximum value of 1 plus out of SRC or 1 plus max in, and that will be the value of out of I. Now once we have calculated the value of out of I, you can compute the value for all of its children as well. So we simply go and call the value for the children, right? So hope this part is clear as well. Now after that, as we mentioned, like we simply take maximum across in and out to get the final maximum depth or maximum distance from this node to any other node in the tree, right? So that's the complete algorithm. One small exercise you can do if you haven't done that yet, try to remove this sort and do it without sort. That will reduce the complexity a lot. And yes, that's all for this video. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.